So let's use this process to find the determinant of a 4 by 4 matrix. We could, if we wanted to, just start off by doing an expansion by minors or a cofactor expansion along any one of the rows or columns. But that will require the evaluation of 4 3 by 3 determinants, which is something that I'd rather avoid if possible. In addition to that, the row reduction process will give us a different perspective on the determinant, which can be very useful. So I'm going to go ahead and row reduce first, being mindful of the fact that I only want to use approved row operations that do not change the determinant of the matrix. So I'm going to replace row 2 with row 2 minus 2 row 1, row 3 with row 3 minus 3 row 1, row 4 with row 4 minus row 1. And let's see what we'll get. 3, negative 2, 1, 5. All right, row 2 minus 2 row 1. 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 All right, row 3 minus 3 row 1. So that's going to be 0. Row 3 minus 3 row 1, I think that's 13. Row 3 minus 3 row 1 is negative 6. And row 3 minus 3 row 1 is negative 10. All right, then it's row 4 minus row 1. All right, so there we've got a significant simplification. And now let's see what else we could do. All right, I'm going to go ahead and use that number as a pivot in its column, and I'm going to use it to clear its column. So I have row 1 goes to row 1 minus row 2 and row 3 goes to row 3 plus 6 row 2. Row 1 minus row 2. All right, row 2 stays the same. Then we're going to have row 3 goes to row 3 plus 6 row 2. So that's going to be negative 16. And then 2, 0, 0, 2. All right. Now, I can take a factor of 2 out of the last row because the determinant is separately linear in each of its rows. So that means proportionality. I could take this factor of 2 out if I wanted to. And now what I'm going to do is use that as a pivot to clear its column. All right? So I'm going to do row 1 goes to row 1 minus 3 row 4. So I would have 0, negative 2, 0, 3. And then I've got 0, 0, 1, negative 1, 0, 13, 0, negative 16, and then 1, 0, 0, 1. Now, of course, if all I wanted was the determinant of this matrix, it would be very easy to find at this point. We could just do a cofactor expansion along the first column. But I want to go a little bit further to point something out. All right? So I need now to use another pivot, and I'm going to go ahead and use this one, even though, oh, I forgot my 2. Even though it's going to be a little bit messy. All right? So I need to replace row 3 with row 3 plus 13 halves row 1. All right? So let's see what we've got. So we add 13 halves row 1, and that caused that to go to 0. Then we're going to have a 0 here, and then I'll have minus 16 plus 39 halves. So what is that? That appears to be 7 halves. All right, and then I'll have 1, 0, 0, 1. But I've still got this 2 here, which actually makes it kind of nice. I could, if I wanted to, now use this as a pivot to clear its column. Notice that it won't change any of the other numbers. So I could replace row 1 with row 1 minus 3 times 2/7 row 3. It doesn't matter. The only thing that's going to happen is this will go away. So I'm just going to do that real quickly. This pivot is going to clear its column. I'm going to let this 2 come back inside. Remember that 2 came from here. All right? Where I'm just again using the linearity of the determinant in each of its rows. Now what I'd like to do is swap the rows to change this into a diagonal matrix. All right, I'm going to swap the 4th and the 1st row. All right, and I'm also going to swap these other 2. So I would have 0, 0, 0, 7 halves, 0, 0, 1, 0, and then 0, negative 2, 0, 0. I did 2 row swaps, so that means that it doesn't change the sign. Now I'll go one more by swapping the 2nd and 4th. All right? Now, each of these rows, I could take that number out. But these numbers are the pivots. That's literally what those those numbers are. And if I took those numbers out, I would get the identity matrix. The determinant of the identity matrix is defined to be 1. So the determinant of this matrix is equal to -14. But it gives us this nice general perspective. The determinant of a matrix is equal to -1 to the power of the number of swaps we need to make in order to row reduce the matrix to the identity times the product of the pivots of the matrix. So we can imagine taking the determinant as just a process of row reducing the matrix to the identity and keeping track of any swaps or scaling factors that we needed to use in order to do that. This also gives us an easy way to establish that the determinant of a product of 2 square matrices is equal to the product of the determinants of those matrices. This also implies that the determinant of BA is equal to the determinant of AB, even though there is absolutely no reason to expect matrix BA to be equal to matrix AB. Matrix multiplication is not commutative, but the determinant of the 2 matrices that we get will be the same.